Sound is a wave, not a thing you can block. Yet your headphones promise silence. How do they make noise disappear? They add another wave that fights the first. Imagine two waves meeting and canceling each other out. That's what happens inside an ear cup. But why does this work only at certain frequencies? And how fast must the new wave arrive to beat the original? The answer lies in timing, phase, and tiny microphones. These microphones pick up every hiss, hum, and buzz from outside. Then a digital brain flips that sound 180 degrees. It sends the inverted wave back into the cup. When the two waves meet, they cancel. But this magic only works when the timing is perfect. What happens if the timing slips? That's the secret we'll uncover. Now that you know the idea of a counterwave, let's break it down step by step. First, sound travels as pressure changes in air. Second, microphones inside the headphones capture those changes. Third, an onboard processor calculates the opposite wave. Finally, the headphone emits this inverted wave so the two cancel out. Keep listening to see how each part works together. Noise cancellation is a technology that reduces unwanted sounds. Passive isolation blocks sound by physical barriers in the ear cups. Active noise control uses microphones to listen to external waves. The headphones generate a second wave that is out of phase. When the two waves meet, they cancel each other out. This cancellation removes most low-frequency rumble from the listener. Higher-frequency sounds are less affected by phase cancellation. Passive isolation still plays a role in blocking sudden loud noises. Together, passive and active methods create a quiet listening environment. Understanding these mechanisms helps users choose the right headphones for their needs. Next, we will explore how sound waves travel through air and into our ears. Pause 0.8 Sound travels as pressure waves through the air. Each wave has a frequency that determines its pitch. Frequency is measured in hertz, or cycles per second. Amplitude represents how loud a sound wave feels. Higher amplitude means louder sound and more energy. Phase tells where a wave starts relative to time zero. When two waves overlap, their phases decide interference patterns. Constructive interference adds amplitudes, making the sound louder. Destructive interference subtracts amplitudes, reducing or canceling sound. Noise-canceling headphones create a wave that is out of phase. The anti-wave meets ambient noise, producing destructive interference. This cancellation leaves the listener with near-complete silence. Pause 0.8 Sound waves travel from a speaker through the air. They propagate as compressions and rarefactions in molecules. When these waves reach the headphone cup, they enter the ear canal. The cup acts like a small waveguide, shaping the sound path. External noise can interfere with internal signals at multiple points. At the cup surface, some energy reflects back into the air. Inside the ear canal, waves may reflect off the eardrum and bones. These reflections create standing waves that alter perceived sound. Noise-canceling headphones generate counterphase waves to cancel external noise. The cancellation occurs before the wave reaches the eardrum, reducing interference. Thus, the ear receives a cleaner signal with less background disturbance. Pause 0.8's foam inside headphone cup acts like a sponge for sound. When a wave hits the foam, its energy is absorbed and spread out. The absorbed energy turns into tiny heat vibrations that dissipate quickly. Silicone seals the outer edge, preventing air from leaking around the ear. This tight seal creates a physical barrier that blocks incoming waves. The remaining sound that reaches the eardrum is much weaker and less disruptive. Because of this, our brain receives fewer external cues to process. The result is a calmer auditory environment that supports focus and rest. Passive isolation relies solely on materials, not electronics, or active cancellation. Understanding these layers helps us appreciate how simple design reduces noise. Pause 0.8's active noise cancellation works by creating a sound wave that is the exact opposite of the incoming noise. Microphones on the headphone pick up the external sounds before they reach your ears. The captured sound is fed into a tiny processor that flips its phase by 180 degrees. This inverted wave travels through the speaker and meets the original wave inside the ear cup. When two waves of equal amplitude but opposite phase collide, They cancel each other out. The result is a dramatic drop in the sound that reaches your inner ear. You still hear music from the headphones, but ambient noise is largely suppressed. This process happens in real time, so you never notice a pause between the external and internal sounds. The key to effective cancellation is matching the amplitude of the anti-wave to that of the incoming wave. If the amplitudes differ, the waves will not cancel perfectly and some noise remains. Pause 0.8 microphones inside noise-canceling headphones are tiny, but essential. They pick up every external sound wave that reaches the ear cup. The captured signal is converted from pressure to an electrical voltage. This voltage travels through a microchip to a digital processor. The processor analyzes the waveform in real time, looking for patterns. It then generates an inverse wave that will cancel the incoming sound. When both waves meet, they interfere destructively and reduce perceived noise. Because the microphone is close to the ear, latency stays below 1 millisecond. That low delay ensures the cancellation feels immediate and natural. Thus, a simple microphone turns ambient noise into silence for the listener. Pause 0.8 first. We capture the incoming noise waveform. Next, a digital filter delays this signal slightly. The delay aligns the wave with its future counterpart. Then we invert the delayed wave to create antiphase. Inversion flips every point of the waveform's amplitude. Now both waves travel toward the headphone drivers together. When they meet, their peaks cancel each other out. The result is a near zero sound pressure at the ear. This cancellation works only if timing and amplitude match perfectly. Digital filters fine-tune both aspects to achieve that precision. The waveform editor visualizes each step for clarity. Pause 0.8's active noise cancellation works by generating sound waves that are the exact opposite of ambient noise. When these two waves meet, they interfere destructively and cancel each other out. Low-frequency sounds have long wavelengths, making them easier to predict and counteract. High-frequency noises change rapidly, so the ANC system struggles to keep up. Typical headphones achieve about 20 dB of attenuation in the 100-500 Hz range. In the 2K Hz to 8K Hz band, attenuation drops to roughly 10 dB. This drop explains why you still hear hiss or clicks at higher pitches. Battery consumption rises when ANC is active because the system must process audio continuously. Manufacturers balance performance with power by limiting ANC duration in battery-saver modes. Thus, users trade off maximum silence for longer listening times. Pause 0.8's ANC works by detecting ambient sound, creating an opposite wave, and canceling noise through destructive interference.